The modern air conditioning system requires a compressor, a condenser, refrigerant, chemicals, copper tubing, an electrical grid, and a monthly bill. In 400 BC, Persian engineers achieved the same result with a hole in the ground, a dome made of goat hair and egg whites, a wall facing south, and the cold of outer space radiating through a cloudless sky. One of these systems costs $187 billion a year. The other costs zero. Make it make sense. Let me tell you exactly what you are paying for when you turn on your air conditioner. The global air conditioning market is valued at $187 billion as of 2025. That number comes from MMR statistics, and it is projected to exceed $300 billion by 2032. In the United States alone, air conditioning accounts for approximately 19% of all residential electricity consumption, 254 billion kilowatt-hours per year, according to the U.S. Energy Information Administration. The International Energy Agency has gone further, stating that cooling, mostly air conditioning, consumes roughly 1/5 of all electricity used in buildings. Worldwide, 1/5, for one function, keeping air cold, the average American household's electricity bill from June through September, the 4 months when air conditioning runs hardest, is $719. That figure comes from Smart Cities Dive, citing federal energy projections, and it represents a nearly 8% year-over-year increase, $719 to survive 4 months of summer. And that number does not include the cost of the unit itself. A central air conditioning system in the United States costs between $3,000 and $7,000 to install, depending on the size of the home and the complexity of the ductwork. The average lifespan of that unit is 12 to 17 years, according to Constellation Energy and Carrier. After that, you replace it, another $3,000 to $7,000. And between installations, you pay for annual maintenance, top-offs, and filter replacements, none of which are optional if you want the system to last even that long. The refrigerant chemicals inside your unit are themselves a story. For decades, the standard was R22, a hydrochlorofluorobenzene that was found to deplete the ozone layer. It was phased out. The replacement, R410A, does not deplete ozone, but it is a hydrofluorocarbon with a global warming potential roughly 2,000 times greater than carbon dioxide. The EPA has documented this. The very chemical that keeps your house cool is accelerating the warming that makes your house hotter. The system creates the problem it claims to solve and then charges you to solve it again. This is not a conspiracy. It is a business model. A subscription to survival. You pay for the unit. You pay for the electricity. You pay for the chemicals. You pay for the replacement. And every year, the summers get longer, the bills get higher, and the planet gets warmer, in part because of the machine humming in your backyard. And 2,400 years ago, in a desert where NASA has recorded the highest land surface temperature in the history of Earth, 159 degrees Fahrenheit, 70.7 degrees Celsius, in the Dashti Lut Desert of southeastern Iran, a civilization figured out how to make ice from water using nothing but physics, mud, and patience. They did not have electricity. They did not have refrigerants. They did not have copper tubing or a grid or a monthly bill. They had observation, ingenuity, and a deep understanding of how the universe actually works. They called their invention the Yakhchal Persian for ice pit, and it is one of the most extraordinary feats of engineering in human history. The year is approximately 400 BC. The Achaemenid Empire, the first Persian Empire, stretches from the Nile River in Egypt to the Indus River in modern-day Pakistan. It is, at this moment, the largest empire the world has ever seen. Its capital, Persepolis, is an architectural marvel of carved limestone, columned halls, and advanced hydraulic engineering. Its road system connects 3 continents. Its postal network delivers messages across 2,000 miles in a week. And beneath the surface of this empire, literally beneath the desert floor, runs an infrastructure so sophisticated that parts of it still function today, 3,000 years later. It is called the Kant system, a network of underground aqueducts that channel fresh water from mountain aquifers to cities, farms, and settlements across the arid plateau. The longest known Kant in Iran, the Zarak Kant in Yazd province, stretches 120 kilometers, roughly 75 miles, with over 2,000 vertical access shafts drilled along its route. Some Kants reach depths of 400 meters. UNESCO designated the Persian Kant system a World Heritage Site, calling it an exceptional testimony to the tradition of providing water to arid regions. It is from this canned water that the Yakhchal was fed. The two systems were connected, the underground river delivering cold, clean water to the ice-making pools adjacent to the Yakhchal dome. And it is in this context, an empire that could move water underground across 75 miles without a pump, that the Yakhchal was born. Not as a novelty, not as an experiment, as a civic utility. Ice was produced, stored, sold in bazaars, delivered to homes, and used to make faluda, a frozen dessert of vermicelli noodles in rosewater syrup that is considered the oldest frozen dessert in the world. The recipe has not changed since 400 BC, 2,400 years, and the same ingredients still work. The Yakhchal was not a rich man's toy by the 1800s, according to German photographer Ernest Holster, who traveled through Persia extensively. There were abundant Yakhchals in Isfahan. Some were private, but the poor could also use them to cool water. Sherbets and fruit were preserved with ice in all shops. Huge chunks of ice were carried by donkeys and sold across the province. Ice in a desert was a public commodity, available to everyone, and it cost nothing to produce beyond the labor of building and maintaining the structure. Now I need to explain the physics, because the Yakhchal does not work by magic. It works by exploiting three natural phenomena that most people alive today have never been taught, even though the science is well documented and peer-reviewed. The three phenomena are radiative cooling, evaporative cooling, and convective heat stratification. The Yakhchal uses all three simultaneously. Here is how. The structure itself is a large conical dome, typically 10 to 18 meters tall, which is 33 to 60 feet. The dome at Maybad in Yazd province stands approximately 15 meters high, with a pit roughly 5 meters deep beneath it. The dome at Moadian Kerman rises to 20 meters, 65 feet. Beneath each dome is a subterranean storage vault. The largest documented vaults reach 5,000 cubic meters in volume. To put that in perspective, that is the equivalent of 2 Olympic swimming pools stacked on top of each other. The walls of the dome are built from a mortar called SRJ, according to Wikipedia, ResearchGate, and multiple architectural studies. SRJ is composed of sand, clay, egg whites, lime, goat hair, and ash mixed in specific proportions. The goat hair functions as a fibrous reinforcement, similar to how fiberglass works in modern composites. The egg whites act as a binding and waterproofing agent. The lime provides hardness. The ash contributes pozzolanic properties. It reacts with the lime over time. To form an increasingly strong, water-impenetrable matrix, the resulting mortar is completely waterproof, thermally insulative, and remarkably durable. Walls built with SRJ are at least 2 meters thick, 6.5 feet, at the base, tapering to roughly half a meter at the apex, where a small vent hole allows hot air to escape. Max Fordham, LLP, a UK-based building physics consultancy, conducted a detailed computational analysis of the Yakhchal at Maybad and published their findings in a peer-reviewed paper presented at the 2017 Passive and Low Energy Architecture Conference. Their modeling revealed something extraordinary. The thermal performance of a 1-meter adobe wall plus 1-meter straw insulation yields a heat transmission U value of 0.1 and a thermal mass value of 150 kilojoules per square meter per Kelvin. This is superficially equivalent to 100 millimeters of concrete plus 400 millimeters of polystyrene insulation, a modern high-performance wall assembly. But the ancient construction actually outperformed the modern equivalent. The scourgeon straw dome produced interior temperatures approximately 3 degrees Celsius cooler than the modern materials with identical numeric properties. The reason is that for very thick walls over 1 meter, it takes approximately 1 full year for heat to propagate through the material. The dome stores the cold of winter inside its walls and releases it slowly throughout the summer. The physics term for this is interseasonal thermal storage, and the Persians were doing it 24 centuries before anyone gave it a name. Now, the ice-making process adjacent to the dome, the Persians built shallow pools, channels roughly 100 meters long, 10 meters wide, and 40 to 50 centimeters deep. Water from the Kant was channeled into these pools at night. Tall shade walls 10 to 15 meters high, oriented east to west, blocked the low-angle winter sun during the day and shielded the pools from warm desert winds. At night, with the walls blocking convective heat gain, the pools were exposed to the clear desert sky. And this is where the critical physics occurs. The desert atmosphere, particularly in the high-altitude plateau regions of Iran, is extraordinarily dry. Low absolute humidity means there is very little water vapor in the air column above the pools. Water vapor is the primary absorber of infrared radiation in the atmosphere. When the humidity is low, the atmosphere becomes nearly transparent too. Thermal infrared, the wavelength of heat radiation emitted by objects on the ground, this means the pool's thermal energy radiates upward, passes through the atmosphere largely unimpeded, and is emitted directly into outer space, where the effective radiative temperature is approximately -270 degrees Celsius. The pool is essentially cooling itself by dumping heat into the vacuum of the cosmos. This process is called radiative cooling, and it is the dominant mechanism by which the Yakhchal makes ice. Simultaneously, evaporative cooling water molecules escaping the pool surface removes additional thermal energy. The combined effect produces a negative energy budget in the pool. The water loses more heat than it gains from the ground and the surrounding air. The water cools to 0 degrees Celsius and freezes even when the ambient air temperature has not dropped below freezing. Max Fordham's numerical simulation confirmed this. Their model, using site-specific hourly climate data from Yazd, predicted that the 400 square meter ice-making pool at Maybad could produce approximately 50 cubic meters of ice in a single winter season. That is roughly equivalent to 3 million modern ice cubes. The ice was formed in layers each night. A thin sheet of water was added, it froze by morning, and another layer was added the next night. When the ice slab reached approximately 50 centimeters thick, it was cut into blocks and carried into the subterranean vault through a low entrance on the north side of the dome. Inside the vault, layers of ice were separated with wood and straw to prevent them from fusing together. A drainage hole at the bottom, often connected back to the cont, carried away any water. The dome itself functioned as a solar chimney. The conical shape caused warm air to rise and escape through the vent at the top, while cool air was drawn in through the base-level entrance. This passive convection kept the interior temperature far below ambient. Some Yakhchals were additionally equipped with Badger's windcatcher towers that captured prevailing desert breezes and funneled them downward through vertical wooden slats into the vault below. The air, already cooled by passing through the underground cant channel, entered the storage space and circulated around the ice blocks. No electricity, no fans, no compressors, just the geometry of a tower, the temperature of underground water, and the movement of wind. And it worked. Max Fordham's simulation predicted that with proper insulation, 1 meter of adobe walls plus 1 meter of straw thatch, only approximately 13% of the ice would melt between January and September. 87% of the ice produced in winter survived the entire desert. Summer, intact, frozen, in a region where surface temperatures can reach 159 degrees Fahrenheit. 129 Yakhchals have been documented across Iran. The number comes from Hemming Jorgensen's comprehensive survey published in his book, Ice Houses of Iran. How, where, why, many are in ruins. But some, like the Yakhchal at Moadai in Kerman, the one at Maybad in Yazd province, and the ice house near the 4,000-year-old cypress tree in Abarku, still stand. Their domes are intact. Their pits are preserved. Their SRJ mortars, mixed from egg whites and goat hair centuries ago, has not cracked, has not crumbled, and has not let water through. And yet the word Yakhchal does not appear in any standard Western textbook on architecture, engineering, thermodynamics, or building science. Not one. Think about what this system represents. A structure that makes ice in a desert using zero external energy. A mortar that outperforms modern insulation assemblies with equivalent thermal properties. A passive cooling system that retains 87% of stored ice through an entire summer without electricity. A civic infrastructure that provided frozen desserts to ordinary people in a region where the ground surface reaches 159 degrees. Now compare this to what the modern world offers. A $1-100-and-$80-7-billion-dollar industry selling machines that last 12 to 17 years require refrigerant chemicals with 2,000 times the global warming potential of CO, consume 1/5 of all building electricity worldwide, and generate a $719 bill every 4 months just to keep your living room tolerable. In 1806, fully 22 centuries after the Persians built their first Yakhchal, an American businessman named Frederick Tudor had what he considered a revolutionary idea. Shipping ice from frozen New England lakes to the Caribbean, he lost 60% of his ice in transit on his early voyages. He was laughed at. He went bankrupt multiple times before finally turning the ice trade into a profitable enterprise. The entire Western concept of refrigeration, the ice trade of the 1800s, the mechanical compressors of the early 1900s, the Freon-based systems of the mid-century, the HFC-laden units of today, developed as though the Persians had never existed, as though no one had ever solved this problem before. But someone had solved it 2,400 years earlier, with mud, hair, eggs, ash, a hole in the ground, and the cold emptiness of outer space. I am not telling you to build a Yakhchal in your backyard. The system was designed for a specific climate: arid, low humidity, with clear skies and cold winter nights. It does not translate directly to Houston or Miami, but the principles translate everywhere. Radiative cooling is now an active field of research at Stanford, MIT, and dozens of universities worldwide. In 2014, a Stanford team led by Shanhui Fan demonstrated a material that could cool to nearly 5 degrees Celsius below ambient temperature in direct sunlight by emitting thermal radiation at wavelengths that pass through the atmosphere and into space. The same physics the Persians exploited with a shallow pool. Thermal mass cooling, storing winter cold in thick walls for summer use, is being rediscovered in the field of interseasonal architecture. Max Fordham's study of the Yakhchal directly informed their recommendations for modern passive building design. Evaporative cooling, the third mechanism in the Yakhchal system, is already used in swamp coolers across the American Southwest, but often without the integration and optimization the Persians applied. The deeper lesson is this: the most expensive solution is not always the best solution. Sometimes it is not even a good solution. Sometimes it is simply the most profitable solution for someone else. The Yakhchal cost $0 to operate. It required no grid connection, no chemical refrigerant, no imported copper tubing, no annual maintenance contract. It was built from materials found within walking distance of the site. It was constructed by local labor using local knowledge. It lasted centuries, and it provided a service, frozen water in a desert, that the modern world requires a $1-100-80-7-billion global industry to replicate, and replicates worse, and charges you for, and breaks after 15 years. In modern-day Iran, Afghanistan, and Tajikistan, the word Yakhchal is still used. It means refrigerator. Every person in those countries, every time they open their kitchen refrigerator to grab a cold drink, uses a word that was invented 2,400 years ago for a dome made of goat hair, and egg whites that froze water using the vacuum of outer space. The machine in their kitchen costs money. The dome their ancestors built did not. The machine in their kitchen will break in 15 years. Some of those domes are still standing after 500. The machine in their kitchen requires a global supply chain of refrigerant chemicals, copper, electricity, and fossil fuels. The dome required sand, clay, lime, ash, goat hair, egg whites, and one clear desert night. One of these systems is considered primitive, the other is considered modern, and yet only one of them is still standing.